Since school, we've learned a simple story. Earth formed, cooled down, a warm ocean appeared, a primordial soup. And there, over millions and millions of years, life slowly began. It sounds reasonable, but here's the catch. Life didn't actually have millions and millions of years. Earth formed 4.5 billion years ago, yet we find the earliest solid evidence of life in rocks dating 3.9 billion years old. Wait a minute. That means life emerged in just 600 million years. Actually, even less than 600 million. For the first few hundred million years, the planet was nothing but a molten ball, a vast ocean of magma. Instead of air, poisonous volcanic gases filled the sky. There was no liquid water. Then, as the surface began to harden, real hell broke loose. For tens of millions of years, asteroids and comets relentlessly pounded the Earth. Each impact packed enough force to instantly vaporize any ocean that might have formed. Total sterilization, complete. And then, as soon as this fiery barrage finally stopped, almost immediately, by geological standards, they appeared. Not just chemical traces, but already complex microorganisms. Here lies the main paradox that puzzles scientists. Time. It simply didn't exist. Imagine a burned-out forest where the ashes have barely cooled, and yet someone has already built a house. Where did it come from? How? This raises a troubling, almost heretical question. What if life isn't native? What if it's a visitor from space? This idea has a name, and it's the title of our investigation, Panspermia. The concept that the seeds of life arrived on Earth from beyond. But to grasp the gravity of this question, we need to dive into the hellish conditions of our planet's earliest days, and understand why life simply didn't have the time to develop here. Making hell is surprisingly simple. Start with a young planet, freshly formed from dust and gas. Heat it until the rock melts into a liquid. You need an ocean of magma, hundreds of kilometers deep. Temperatures reach several thousand degrees. Instead of air, fill it with a thick, suffocating mix of carbon dioxide, methane, and hydrogen sulfide. Imagine the smell of rotten eggs, but on a global scale. This was Earth's first few hundred million years. Geologists call this the Hadean Eon, named after Hades, the ancient Greek underworld. And the name fits perfectly. There's nothing here that resembles life. No solid surface to stand on. No water to drink. Just a fiery, poisonous ball. Over time, the planet began to cool. The oldest minerals, tiny zircon crystals, tell us that about 4.4 billion years ago, the first liquid water may have appeared on the surface. Small puddles forming on a solidifying crust. The very first hint of hope. The planet's first breath as it cooled. And at this moment, the recipe for disaster moved into its second, most brutal phase. Imagine the early solar system as a massive billiard table where the balls, the planets, hadn't yet settled into stable positions. Then, roughly 4,100 million years ago, the two biggest players, Jupiter and Saturn, shifted their orbits slightly. That was enough to unleash total chaos. Their gravity, like a giant player's cue strike, slammed into the asteroid belt. Billions of rocky and icy chunks, from tiny grains of sand to objects the size of small countries, were knocked from their orbits and hurtled toward the center of the system. Straight at us. This set off an era scientists call the Late Heavy Bombardment.
How do we know this with such certainty?
The proof hangs above us every night. The moon. It has no atmosphere, no tectonic plates, no wind, no rain to erase its scars. The moon stands as the perfect witness, its surface preserving a 4 billion year history. Those dark patches we see from Earth, which we sometimes imagine as whimsical faces, they aren't seas. They are vast, frozen lava lakes. Craters from asteroid impacts so powerful they punched right through the lunar crust, letting molten rock pour out through the cracks. When the Apollo astronauts brought back samples of this sea rock, analysis revealed something astonishing. Nearly all of it formed within a narrow window, about 3.9 billion years ago. These weren't random impacts spread across time. It was a concentrated, furious storm of collisions that raged for several 100 million years.
If the moon took such a beating, what about Earth? Our planet is much larger. It attracted far more cosmic debris and faced impacts far more often and with greater force. The disasters were unimaginable in scale. When an asteroid several dozen kilometers wide struck, it unleashed energy thousands of times greater than the entire nuclear arsenal of humanity. Any oceans that might have formed by then simply evaporated. Completely. Imagine boiling a pot of water, but instead of a flame, the heat comes from an explosion the size of a continent. The water turns into steam, creating a dense, scorching atmosphere that blankets the entire planet, literally sterilizing its surface at temperatures of hundreds of degrees. Then, as the steam cools and falls back as rain to refill the oceans, another asteroid strikes, and the cycle repeats, over and over for millions of years. This wasn't just a hostile environment, it was a planetary sterilization system running on a relentless loop. This fiery rain stops around 3.8 billion years ago. The planet finally gets a break. The surface cools down and the oceans stop boiling away. Earth becomes a sterile, lifeless sphere, covered in water and pocked with craters. And then, the strangest thing happens. In the oldest rocks we can find, dated between 3.7 and 3.8 billion years, we discover the first signs of life. More precisely, signs of activity, right in the earliest geological layers that could have possibly survived from that time. Not just hints of organic molecules, but fully formed microorganisms. Judging by the chemical traces and structures they left behind, these creatures already had complex metabolisms. They could process energy, they had mechanisms to copy their genetic code, and they built entire colonies. Today, we find those colonies fossilized as stromatolites. This isn't a blueprint for a house. It's a fully built and inhabited home. Let's do the math. The bombardment ended 3.8 billion years ago. Almost immediately after that, 3.7 billion years ago, we find evidence of complex life. That means the window for life to emerge from non-living chemistry and evolve into a fully functioning cell spans just a few tens of millions of years. Wait a minute. Tens of millions of years? That sounds like an enormous stretch to us. But in the grand timeline of our planet, it's just a blink. Imagine compressing Earth's entire history into a single day, from its birth at midnight to today. That window for life lasts less than 3 minutes. Just 3 minutes for a chaotic mix of chemical elements in a cooling soup to accidentally form the first self-replicating molecule. Then, for it to evolve into a complex cell with DNA, ribosomes, and metabolism. Most biochemists agree that's an alarmingly short amount of time. Abiogenesis is like blindly playing a lottery with astronomical odds. To win, you have to try again and again. Millions, even hundreds of millions of years of trial and error. And Earth simply didn't have those hundreds of millions of years to spare. The picture becomes absurd. Imagine this. You're fighting a massive forest fire. Just as the last ember cools, you turn around, and there, standing on the ashes, is a fully built log cabin. Not a pile of logs, not a foundation, but a complete house. Your first thought wouldn't be, wow, how fast did those trees grow and get cut down? No, your immediate reaction would be, someone brought this here fully assembled. This time paradox is so striking that it has captured the attention of scientists. The idea that life didn't originate here, but arrived from elsewhere, has a surprisingly long and serious history. It's not science fiction. It's a logical conclusion drawn from the dead end that geological and paleontological evidence forces us into. And it makes us reconsider meteorites, comets, and cosmic dust, not as harbingers of destruction, but as possible messengers carrying life itself. The idea that life came from outer space isn't new. Not at all. It's so old that its roots stretch back to ancient times. long before we even grasped what the cosmos really are. The very term panspermia derives from Greek, pan meaning all, and sperma meaning seed. Seeds of everything, scattered across the universe. Back in the 5th century before our era, the philosopher Anaxagoras spoke of homeomeres, infinitely small particles of all existence, drifting through the cosmos. These particles, he said, combine to form worlds. Of course, it was pure philosophy, intuition rather than science. But what's striking is how closely that intuition aligns with the hypothesis that 2,500 years later, some of the greatest scientists would seriously debate. This idea only gained scientific recognition in the 19th century, and that's no coincidence. In 1859, Charles Darwin published On the Origin of Species, Changing the World Forever. Darwin explained how life evolves, but he left one crucial question unanswered. How did it begin? Into that gap, into that void, Panspermia stepped. Just 6 years after Darwin's book, in 1865, German physician and biologist Hermann Richter proposed that the first microorganisms didn't emerge on Earth, but arrived via meteorites. This wasn't a fringe theory. Richter's idea earned support from giants of physics at the time, Lord Kelvin, the man behind the temperature scale bearing his name, and Hermann von Helmholtz, one of the founders of the law of conservation of energy. These were not dreamers, they were builders of modern science, and they saw this hypothesis as a logical solution to a profound problem.
The most elegant version of panspermia emerged in the early 20th century. Its creator was the Swedish physical chemist Svante Arrhenius. His name is worth remembering. Arrhenius stands among the founding fathers of physical chemistry and is a Nobel Prize winner. To be precise, when he first proposed his theory, he hadn't yet won the prize, but he was already a leading contender. He received the award in 1903 for his theory of electrolytic dissociation, a breakthrough that underpins our understanding of how batteries work, how nerve cells transmit signals, in short, about half of modern chemistry and biology. And here was a mind that changed the world, seriously exploring panspermia. That says a lot about the caliber of thinkers this idea attracted. Arrhenius called his theory radiation panspermia. It was incredibly elegant. He understood that light isn't just heat, it also exerts pressure. Yes, sunlight applies a tiny but constant physical force on anything it hits. Think of it as an endless, gentle breeze. Arrhenius calculated that this pressure was enough to lift minuscule particles from a planet's upper atmosphere, like bacterial spores, and literally blow them into outer space. Once caught in the stellar winds of other stars, these spores could drift through interstellar space for millions of years. Eventually, they might stumble into the atmosphere of another planet, like the young Earth. Life hitchhiking on beams of light. It almost sounds poetic. But most importantly, this idea rested on a real, experimentally proven physical phenomenon. It seemed like the perfect solution. Elegant, scientific, and proposed by a future Nobel Prize winner. But this beautiful theory had one fatal flaw. One detail that Arrhenius, at the dawn of the 20th century, simply couldn't fully grasp. That detail was the space between the stars. It turned out to be more than cold and empty. It was deadly hostile. The problem is cosmic radiation. Not the gentle ultraviolet rays we protect ourselves from with sunscreen at the beach. This is harsh, ionizing radiation. High-energy particles streaming from the sun and distant stars. A relentless bombardment that tears apart complex organic molecules. For a defenseless bacterial spore drifting through the vacuum, it's a death sentence. Imagine sending a paper boat into a sea of sulfuric acid. It won't just sink, it will dissolve down to its atoms. Later calculations revealed something shocking. An unprotected spore in open space doesn't get sterilized over millions of years. It happens in mere days, maybe even hours. The Arrhenius theory was elegant, but it's dead. One undeniable fact killed it.
the harsh reality of space turned out far more brutal than scientists imagined 100 years ago. But the idea didn't die with her. It simply shifted. Scientists realized the problem wasn't the concept of life traveling through space, it was how that life was transported. Passengers couldn't ride exposed to the harsh winds of space. They needed a ticket to a cabin. They needed protection. Then they recalled Hermann Richter's original hypothesis: meteorites. A mere few centimeters of rock make the perfect shield against cosmic radiation. This hypothesis came back to life in a new form: lithopanspermia, life hitching a ride inside rocks. The theory of life riding beams of light was dead, but the idea of life hidden in a stone ark was just beginning. And this transport had been falling to Earth long before humans ever arrived, carrying something far more than just rocks and metal. On the morning of September 28, 1969, just before 11 o'clock, the sky above the small Australian town of Murchison suddenly split open. A fiery ball, brighter than the sun, streaked across the sky and exploded with a deafening roar that shattered windows and homes. Black, molten stones rained down to the ground. Altogether, these cosmic fragments weighed over 200 pounds. It was an incredible stroke of luck. If the meteorite had fallen into the ocean or a remote desert, we would never have uncovered its secrets. But the people of Murchison, captivated by the event, began collecting the pieces almost immediately. Some stones still smelled of ozone and felt warm to the touch. This was the freshest, purest meteorite scientists had ever held, and they wasted no time starting to examine it right away. What they found inside defied understanding at first. The rock, classified as a carbon-rich chondrite, porous like a sponge and packed with carbon, contained organic matter. Lots of it. In total, more than 14,000 different organic compounds. But the real shock came with the discovery of amino acids, the very building blocks that make up all proteins, the foundation of every form of life we know. That's when the numbers stopped matching anything we see on Earth. Wait, scientists found more than 70 types of amino acids in the meteorite, but every living thing on Earth, from viruses to blue whales, builds its proteins from only 20 standard amino acids. So where did the other 50 come from in this rock? If it were just ordinary Earth contamination, if the stone had simply absorbed bacterial remains from soil, we would have found our familiar standard set of 20 amino acids. But here, something else was at play. Something completely alien. This was the first, but far from the last, piece of evidence. Scientists conducted an isotope analysis of the carbon in these amino acids. To put it simply, carbon atoms come in light and heavy versions. On Earth, their ratio stays consistent. But in the meteorite's amino acids, there were significantly more heavy isotopes. It was a chemical fingerprint, clearly stating, "Not made here." The meteorite itself dated back 4.6 billion years, making it the same age as our solar system. But wait, in 2020, researchers discovered something even older inside it: pre-solar grains, tiny dust particles ejected by other stars long extinct. This package had been sent before our sun was even born. But that wasn't the main discovery. Amino acids are the building blocks of proteins, the cell's machinery. Yet, to create life, you need instructions, blueprints. You need the genetic code in DNA or RNA. After decades of analyzing the Murchison meteorite with increasingly advanced instruments, scientists finally found what they were searching for. It contained all 5 nucleobases: adenine, guanine, cytosine, thymine, and uracil. Every single one, the letters that make up the genetic alphabet of all life on Earth. Space didn't just send us building blocks, it delivered the complete set needed to assemble life's most essential molecule. The discovery of the Murchison meteorite completely changed the game. The idea that Earth was a unique cradle of life, and that life itself was a lucky accident in a primordial soup, collapsed. Suddenly, it became clear that space is not a sterile void. It's a vast chemical factory, churning out the raw materials for life on an industrial scale. That doesn't mean fully formed bacteria are flying through space. Far from it. But it does mean that their building blocks travel across the cosmos in huge quantities. From this insight came a new, more cautious version of panspermia, molecular or soft panspermia. Space doesn't deliver life itself, it delivers the components that make life possible. The evidence seemed airtight, but skeptics held on to one last powerful argument. Yes, the meteorite was collected quickly, but it still fell to Earth. It rested on Australian soil, breathed Earth's atmosphere. What if this porous rock absorbed not living bacteria, but microscopic remains of ancient terrestrial organic matter, built up over billions of years in soil and dust, just like a sponge? What if it was actually a cleverly disguised contamination? To settle this once and for all, scientists needed a sample that never touched our planet, a package intercepted straight from space. Humanity had to send a probe hundreds of millions of miles away to retrieve it. The mission was clear: bring back a sample from an asteroid that had never touched Earth, a package from deep space, sealed in a vacuum. The Japanese probe Hayabusa 2 set out to retrieve it. Its target was Ryugu, a dim, rocky body the size of a small hill, spinning hundreds of millions of miles away. This was the only way to settle a decades-long debate over Earth's contamination once and for all. The probe arrived at Ryugu in 2018. What followed felt more like a Hollywood script than a scientific mission. They couldn't just land and scoop up soil. The surface of any asteroid has been blasted for billions of years by solar wind and cosmic rays, breaking down complex organic material. They needed samples from beneath the surface, pristine, untouched. But how do you reach that? The answer was brilliantly simple. Shoot at the asteroid. Hayabusa 2 released a small impactor, a 2-kilogram copper projectile, and then hid behind the asteroid's horizon. After the explosion created a fresh crater, the probe returned and collected material from the dust cloud kicked up by the blast. For a year and a half, it circled Ryugu, studying and gathering samples. In December of 2020, a tiny capsule plunged through Earth's atmosphere and drifted down by parachute into the Australian desert. Inside lay a treasure that scientists had chased for 6 years: 5 grams of dark material from the Ryugu asteroid. To be exact, 5.4 grams. A teaspoon of dust worth billions of dollars, traveling 5 billion kilometers across space. When researchers opened the capsule in a sterile lab, silence fell over the room. The findings exceeded every expectation, even the boldest ones. Scientists found more than 20 different amino acids in samples from Ryugu. What's even more remarkable is that some of these amino acids are used by life on Earth, while others don't exist anywhere on our planet. Contamination was ruled out. These molecules formed in space, and now we have the proof. But that was just the beginning. The dust also contained uracil, a crucial building block of RNA, the predecessor to DNA. They found nicotinic acid too, known to us as vitamin B3, essential for metabolism in every living organism on Earth. Space wasn't delivering random scraps. It was supplying complex, functional components. While the scientific community was still processing this news, independent confirmation arrived. The American spacecraft OSIRIS-REx, which had been studying a different asteroid called Bennu, was also returning home with samples. Once scientists analyzed those samples, the picture became even more astonishing. The soil from Bennu contained not only 14 of the 20 amino acids found on Earth, it held all 5 nucleobases. Wait, all 5? Adenine, guanine, cytosine, thymine, and uracil. Every single letter that makes up the genetic code of all life on Earth. The Murchison meteorite delivered us nearly a complete set of Lego bricks. Bennu sent the entire set, extra pieces included. There was no longer any doubt. The hypothesis of molecular panspermia had become a proven fact. Space is a massive chemical factory, crafting the building blocks of life according to universal recipes. At the dawn of its history, young Earth was literally showered with this cosmic cargo. The question of whether life's components could have arrived from space was settled. The answer? Yes, they did. They came from the stars. But this discovery sparked an even bigger question. Okay, space delivers parts, molecules, chemical precursors. But could it deliver something more? Not a kit to assemble, but a fully built model? Not amino acids, but a living cell? That idea seemed pure science fiction. The gap between complex organic molecules and the simplest organism is enormous. Yet, one finding briefly made the world believe that this gap might be bridgeable. That perhaps, once, a rock fell from the sky carrying not just the promise of life, but its fossilized trace. In 1984, deep in Antarctica's icy desert near the Allen Hills, a team of meteorite hunters discovered an unremarkable greenish rock. It weighed just under 4.5 pounds, about the size of a large potato. They labeled it ALH 84001 and shelved it. For 10 years, it just sat there, an ordinary stone. Then, in 1994, someone decided to take a closer look. Inside, they found tiny bubbles of frozen gas. When scientists analyzed their composition, they couldn't believe their eyes. The gas wasn't Earth's air. Instead, its makeup matched the atmosphere of Mars exactly, as measured by the Viking lander back in 1976. That dusty rock, forgotten for a decade, turned out to be a visitor from another planet. The reconstruction of its journey is astonishing. Long ago, perhaps 16 million years back, a colossal asteroid slammed into Mars. The impact was so powerful it blasted chunks of the Martian crust into space. One of those fragments, our rock, drifted through the solar system for millions of years until, about 13,000 years ago, its orbit crossed Earth's path. It crashed into Antarctica and lay frozen in the ice, waiting for its moment. And that moment came. On August 7, 1996, a team of NASA scientists led by David McKay held a press conference that shook the world's media. They announced that inside the meteorite ALH 84001, they had found compelling evidence of ancient Martian life. Not just organic molecules, but a whole set of clues. 4 of them, to be exact. First, there were carbonate spheres, known as globules. On Earth, these structures often form through bacterial activity. Second, scientists found complex organic compounds called polycyclic aromatic hydrocarbons. These are what remain after microorganisms break down. Third, they discovered tiny magnetite crystals, an iron mineral. Their shape and purity matched crystals produced by certain Earth bacteria, which use them as an internal compass. And fourth, the most compelling clue, under an electron microscope, researchers saw shapes resembling fossilized nanobacteria, tiny, segmented, worm-like forms, a ghost of life etched in a Martian rock. Pause for a second. Really take in the scale of this announcement. It wasn't some tabloid or a UFO enthusiast. It was NASA. So confident in their findings that the President of the United States himself spoke about it. Bill Clinton delivered a special address right from the White House lawn, calling the event inspiring. For a brief moment, the world believed that the greatest question in human history, are we alone in the universe, had been answered. And the answer was no. But science doesn't work that way. Extraordinary claims demand extraordinary evidence. The scientific community began scrutinizing the findings of the McKay team with intense skepticism. Years of heated debate followed, and one by one, all 4 pieces of evidence unraveled. Carbonate globules? It turns out they could have formed at extremely high temperatures, triggered by the shock of an impact that blasted the rock off Mars. In those conditions, any life would have simply boiled away. Organic compounds, polycyclic aromatic hydrocarbons? Yes, they were there. But similar molecules appear in other meteorites and even in interstellar dust. The biggest problem? Antarctic ice. And practically any Earth-based lab is teeming with these same terrestrial contaminants. Proving the Martian origin of these molecules was impossible.
What about the magnetite crystals? Other researchers demonstrated that similar crystals can form without any life involved, created purely by chemical reactions during the same shock heating. That left only the so-called fossils. The most striking evidence turned out to be the weakest. These structures were incredibly tiny, ranging from just 20 to 100 nanometers in length. To put that in perspective, they were hundreds of times smaller than any known bacterium on Earth. Most scientists agreed these were far too small to hold even the bare essentials for life. No genetic code, no ribosomes, no proteins. They were likely just unusual mineral formations, light and shadow playing tricks on the stone's rough surface. The ghost wasn't there. The final chapter in this story was written just recently, in 2022. A team of researchers led by Andrew Steele examined a meteorite using technologies that simply didn't exist back in the 90s. They proved that all the organic material in the rock formed through two well-known geochemical processes: serpentinization and carbonization. Water seeping through cracks deep beneath Mars's surface reacted with basalt, creating that organic matter. No life involved, just pure chemistry. So, was this whole story just a loud failure? A scientific mistake blown way out of proportion? Not at all. The story of the ALH 84001 meteorite, even though it didn't bring us aliens, remains one of the most important discoveries in astrobiology. It was the first undeniable proof that matter can travel between planets, that rocks really do fall from Mars to Earth. It showed us that 4 billion years ago, Mars held water and complex organic chemistry. These aren't just theories, they're facts we can hold in our hands. That rock forced science to develop much stricter criteria for searching for life, criteria we still use today. Thanks to this so-called failure, we became far wiser. The story of this stone settled the question. Can rocks travel between planets? Yes, they can. But it opened an even tougher question. The rock can survive the journey. What about its passenger? Can anything alive endure a blast powerful enough to eject it from a planet, then survive millions of years frozen in the vacuum of space, and finally, the fiery plunge back through an atmosphere? The champions of survival live right here on Earth. We didn't have to look to alien worlds for examples. Meet the tardigrade. Also known as the water bear, this microscopic creature measures less than a millimeter long. It has 8 legs and looks like a clumsy vacuum cleaner bag with feet. And it might just be the toughest animal on the planet. Its secret weapon? Cryptobiosis. When conditions become unbearable, the tardigrade almost completely dries out, losing up to 97% of the water in its body. Its metabolism slows to nearly zero. It turns into a tiny, lifeless speck of dust. In this state, it can survive almost anything. In 2007, scientists set out to find what almost everything really means. They sent a group of tardigrades into space aboard a Russian satellite called Photon M3. The tiny creatures were simply exposed to the vacuum. 10 days drifting outside in space. 10 days under harsh ultraviolet light, cosmic radiation, freezing vacuum, and extreme temperature swings. When the satellite returned to Earth, researchers collected the dried-out tardigrades, added water, and waited. Then, they came back to life. But here's the most astonishing part. They didn't just survive. They started reproducing and produced perfectly healthy offspring. A multicellular animal survived open space and had babies. That fact alone changes everything. The tardigrade is a remarkable creature. But what about more likely travelers? Bacteria? Among them, there's a true superhero. Its name is Deinococcus radiodurans. The Guinness World Records lists it as the most radiation-resistant form of life. To put that into perspective, a dose of 5 to 10 gray would kill a human.
This bacterium can survive 5,000 gray. Imagine standing at the epicenter of a nuclear explosion and still dividing. Its secret isn't some kind of super armor. Instead, it relies on an incredibly efficient DNA repair system. Radiation shatters its genetic code into hundreds of pieces, but special proteins piece it back together, like the most complex puzzle on Earth, in just a few hours. But can life survive the actual moment of breaking away from a planet? The pressure is immense. In the lab, scientists compress Deinococcus cells under 30,000 atmospheres of pressure. That's 30 times greater than at the bottom of the Mariana Trench. 60% of the cells survived. And this isn't an isolated case. Spores from ordinary moss clung to the exterior of the International Space Station for 283 days. When they returned to Earth, 86% of them sprouted without trouble. Life clings to survival with a stubbornness that's hard for us to imagine. Sure, they can survive a short trip, but a journey from Mars to Earth takes millions of years. The biggest threat in that journey isn't the vacuum of space, it's the sun's ultraviolet radiation, which sterilizes all living things. You might think the solution is a thick shield, several meters of rock. That would mean only those trapped inside a large meteorite have a chance. But a Japanese experiment called Tanpopo on the International Space Station revealed something surprising. They placed pellets containing Deinococcus bacteria on an external platform of the station. Then they left them exposed for 3 years. When the granules returned to Earth, scientists discovered the top layers of bacteria had died. They absorbed the full brunt of ultraviolet light and radiation, but in doing so, they formed a thin, dark crust. This crust, made of lifeless cells, became a shield for those beneath it. And get this, the shield was only 0.5 millimeter thick. Actually, even less. Calculations revealed that a 0.5 millimeter layer can protect a colony for up to 8 years in open space. Inside a rock, even a small one, that protection could last hundreds of thousands of years. They don't need a massive asteroid. These microbes shield themselves, using their fallen comrades as armor. Now, let's piece it all together. The journey of a microbe from Mars to Earth faces 3 deadly challenges. Test 1. Ejection. An asteroid slams into Mars, triggering a massive explosion. Yet not all debris blasted into space heats up to white-hot temperatures. Rocks from the edges of the impact crater might be ejected relatively gently, escaping sterilization. We know bacteria can survive the intense pressure of such an impact, so there's a real chance for life to endure this first trial. Test 2. The journey. The rock drifts through space. This voyage can last anywhere from tens of thousands to millions of years. Radiation poses the greatest threat, but even a layer of rock, or a shell of dead cells, can act as a shield. For bacteria in spore form or cryptobiosis, time hardly matters. Their internal clocks stop, so they can survive this stage as well. Test number 3. The fall. A meteorite plunges into Earth's atmosphere at speeds of tens of kilometers per second, turning into a fiery blaze. But here, ablation kicks in, the same process that shields returning astronaut capsules. The outer layer of the rock burns away and vaporizes, carrying almost all the heat with it. Meanwhile, the meteorite's core can stay surprisingly cold. Cold enough that freshly fallen meteorites often show a coating of frost when discovered. So, if you're inside, surviving the fall is possible. Breakaway, flight, fall. Each stage poses a deadly threat. The chance of making it through any one of them is incredibly slim, but it's not zero. And on the scale of the solar system, where over billions of years millions of such collisions have occurred, a not zero chance becomes almost a certainty. Modern science has reached a striking conclusion. The physical possibility of life traveling between planets within our solar system, for example from Mars to Earth, is now proven. This is no longer science fiction. It's a viable scenario. Life can survive in space, and rocks can carry it. This turns the idea of panspermia from a mere hypothesis into a working model. But some scientists have gone even further. One of them, a pioneer who helped unlock the secret of life itself, looked at the complexity of the genetic code and suggested something remarkable: that none of it happened by chance. That the seeds of life weren't just scattered by the wind. Someone planted them on purpose. His name was Francis Crick. Yes, the very same Crick who, alongside James Watson, won the Nobel Prize for uncovering the structure of DNA, the man who decoded the language of life. Now, standing at the pinnacle of the scientific world, he looked at his greatest discovery and said, "This can't be." He couldn't believe that a molecule of such staggering complexity, carrying gigabytes of information, could have arisen by pure chance in a warm puddle. Statistically, by his calculations, the odds were almost as slim as a tornado sweeping through a junkyard and assembling a Boeing 747 out of the debris. This paradox haunted him relentlessly. Then, in 1973, scientist Francis Crick and his colleague Leslie Orgel made a move that stunned the scientific community. They published a paper in the journal Icarus titled Directed Panspermia. Their hypothesis sounds like the plot of a Hollywood blockbuster. Long ago, in a galaxy far, far away, an advanced civilization, possibly on the brink of extinction, decided not to save itself, but to save life itself. They packaged simple microorganisms into what you might call cosmic care packages and sent them to young star systems with planets resembling our own. A message in a bottle. But instead of a bottle, it was an asteroid, and instead of a message, it was DNA itself. Sounds crazy? Maybe. But Crick wasn't one to throw words around lightly. He needed proof. Something that could confirm life on Earth came from outer space. And he found it. Or at least, he thought he did. That clue was molybdenum, a fairly rare metal in the Earth's crust. But here's the strange part. It's absolutely essential for certain key enzymes that make our biochemistry work. Every living thing on Earth, from bacteria to elephants, depends critically on this rare element. Imagine if every car on the planet ran on a fuel you could only find on one tiny island in the Pacific Ocean. Francis Crick approached the problem like a detective. Why would evolution rely on such a rare element? Wouldn't it make more sense to use something more common, like chromium or nickel, which are right under our feet? Crick believed the answer was simple. Evolution didn't choose. It inherited this biochemical engine fully assembled. The dependence on molybdenum didn't develop here on Earth. It originated on another planet, where this element was abundant. Life came to Earth already carrying this built-in, unchangeable trait. Molybdenum is like an accent that instantly identifies a foreigner. A chemical signature left at the crime scene. A mark that says, "I don't belong here." Of course, this elegant theory has a major flaw. Critics were quick to spot it. They pointed out something obvious. The directed panspermia hypothesis doesn't solve the mystery of life's origin, it just shifts the question somewhere else. Fine, let's say life was sent to Earth by them. But how did life begin with them? Was it sent to them by someone else? And who sent life to those senders? This creates an endless chain with no clear starting point. The question of where did life come from simply turns into where did the gardeners come from? It's a clever way to dodge the answer. Intellectually neat, but still a dodge. Crick's idea remained brilliant, but unprovable. It was the intellectual challenge of a genius, daring to question the very foundations. While biologists and philosophers debated the concept of cosmic gardeners, another group of scientists took a completely different approach. They weren't searching for signs of intelligence. Instead, they simply looked through their telescopes. What they observed in the light spectra from distant comets would change everything once again. In the late 1970s, astrophysicist Fred Hoyle and his colleague Chandra Wickramasinghe noticed something unusual. They were studying how interstellar dust absorbs light from distant stars. This absorption spectrum acts like a chemical fingerprint of the material. But this fingerprint didn't match any known minerals or ices. Instead, it eerily resembled the spectrum of dried bacteria. The idea was so radical that most scientists just dismissed it, but Hoyle couldn't shake it off. From this single, controversial observation, he built an entire theory. If the dust between stars contains complex organic molecules, then the objects formed from this dust must be real treasure troves. We're talking about comets, of course. Hoyle suggested that these icy worlds aren't just lifeless chunks of rock. He called them incubators. Beneath their thick layers of ice, simple molecules, warmed by rare rays of the sun, could react, gradually forming more complex compounds. For Hoyle, comets acted as cosmic sowers, spreading not life itself, but all the chemical ingredients needed for it. For many years, this idea was dismissed as eccentric nonsense. Then, we learned how to fly to comets. In 1986, the European probe Giotto pierced through the gas and dust clouds surrounding Halley's Comet. Its instruments detected a vast array of complex organic molecules. Not bacteria yet, but the very prebiotic chemistry Fred Hoyle had predicted. Almost 20 years later, in 2005, NASA's Deep Impact mission took things further. It fired a 370-kilogram projectile at Comet Tempel 1. More precisely, the projectile was copper, specially weighted to break through the icy surface. The impact blasted material from deep inside the comet into space. Analyzing that cloud revealed not just water, but also precursors to amino acids, the fundamental building blocks of proteins. It was a triumph. Suddenly, the whole picture of how life began on Earth became clearer and more vivid. We had literally cracked open a comet and found a chemical factory inside. Then, further calculations landed another blow. During Earth's early history, comets delivered 20 times more organic material than asteroids. Not 20%, 20 times. This meant that the delivery of life's building blocks wasn't a rare, lucky accident. It was a steady downpour of organic material lasting millions of years. The chances that life would assemble somewhere from this cosmic toolkit shot up dramatically. Fred Hoyle turned out to be a prophet whose predictions came true during his lifetime. That should have been the end of the story, with him receiving every possible honor. But it didn't end that way. Confident in his convictions, Hoyle took a bold next step, a step into the abyss. He claimed that comets bring us more than just organic molecules. They also carry fully formed viruses and even bacteria. He seriously argued that Earth's annual flu epidemics result from our planet passing through the dusty tails of comets. He called this phenomenon the cosmic flu. And that's when he crossed the line. The boundary between a testable scientific hypothesis and pure fantasy. His theory about the chemistry of comets rested on solid ground: spectral data, instrument readings, results from space missions. But the so-called space flu had nothing behind it. No evidence, no way to verify it. The scientific community, which he had almost convinced with great effort, recoiled in horror. His name, once a symbol of bold thinking, became synonymous with pseudoscience. The man who gave us a crucial piece of the puzzle about the origin of life ended up destroying his own legacy. It's a tragic story about a genius who couldn't stop in time. Fred Hoyle's story proved one thing. Comets aren't just frozen chunks of ice. They act as vital highways, carrying the building blocks of life across the entire solar system. But until now, we only talked about travel within our own cosmic neighborhood. Could life hitch a ride between stars? Until 2017, that idea was pure theory. Then, an unexpected visitor crashed into our system, one that showed these interstellar journeys are real. And this visitor looked nothing like we expected. On October 19, 2017, a computer at the Pan-STARRS Observatory in Hawaii detected a faint point of light. It wasn't an asteroid, a comet, or anything listed in our catalogs. The object followed a hyperbolic trajectory, which means it wasn't orbiting the sun. It had come from beyond, from the vast darkness between stars, and was heading back out there, never to return. For the first time in history, we had spotted a visitor from another star system. They named it Oumuamua, a Hawaiian word meaning scout or messenger arriving first from afar.
And this visitor behaved in a very, very strange way.
First, its shape. Brightness data revealed the object was highly elongated. How elongated? Its length was about 10 times its width. This wasn't a rock. It was a cigar. Or, as some later suggested, a flat pancake. Nothing like this had ever been seen in our solar system. But the shape was just the beginning. The real mystery lay in its motion. Oumuamua was moving away from the sun faster than it should have. Some additional force was acting on it, beyond gravity. At first glance, the explanation seemed obvious. It had to be a comet. When a comet approaches the sun, its ice vaporizes, creating a jet-like thrust. That's where the non-gravitational acceleration comes from. But here's the catch. Oumuamua had no tail. None at all. Telescopes found no gas cloud, no dust halo, the coma that usually surrounds a comet. The object sped up like a comet, but it wasn't one. Imagine spotting a boat moving upstream, without oars, without sails, without an engine. Something was propelling it forward, but no one could see what. Enter Abraham Loeb, an astrophysicist from Harvard. He asked a simple but provocative question. What if we're looking for the wrong thing? What if this wasn't a natural object? Loeb proposed that Oumuamua might be artificial, perhaps a solar sail, a thin sheet of material pushed forward by the pressure of sunlight. More than just a guess, he published calculations showing that this technology could explain its shape, its unexpected acceleration, and the lack of a comet's glowing tail. Most scientists met this idea with skepticism. They offered other, stranger natural explanations, like a fragment of a nitrogen iceberg or frozen hydrogen. But the very fact that the artificial origin hypothesis appeared seriously in a scientific journal says just how extraordinary this visitor was. But let's assume Oumuamua is just a rock, an ordinary, natural, interstellar rock. Could life survive on it? The journey between stars takes tens of thousands, sometimes even millions of years. During that entire time, the object faces a relentless barrage of galactic cosmic rays, harsh radiation strong enough to sterilize even a rock a meter thick, wiping out any DNA. The chances that life could survive such a trip are vanishingly small. But here's the crucial point. No matter what Oumuamua really is, whether an alien probe, a nitrogen iceberg, or simply a strange rock, its very existence proves one thing. Interstellar exchange of material is real. Objects from other star systems truly do visit us. That means the universe isn't a collection of isolated islands. It's a vast ocean, drifting with messengers. The mystery of Oumuamua remains unsolved. It vanished into the darkness, leaving us debating its true nature. But while we kept our eyes on the sky, searching for visitors from other worlds, we missed something far more important. Here's the ironic twist. We haven't been just passive observers all along. In fact, we've become the ones sending messages, without even realizing it. Some places on Earth demand absolute sterility, almost as sterile as outer space. NASA's clean rooms are one such place. There, under the strictest conditions, scientists assemble spacecraft destined for other planets. The air filters hundreds of times every hour. Everyone wears protective suits that look like spacesuits. Every surface is treated with the most powerful disinfectants. The goal? To make sure no earthly microbe accidentally hitchhikes its way to Mars or Europa. But it was exactly in these man-made temples of cleanliness that scientists found something they never expected. NASA's clean rooms harbored 26 previously unknown species of bacteria. These aren't just random microbes that slipped through by accident. They're true survival champions. These bacteria resisted standard sterilization methods, including intense ultraviolet radiation and chemical disinfectants. By creating a harsh, life-hostile environment, NASA engineers unknowingly triggered accelerated evolution. They built the perfect testing ground to select the toughest microorganisms on Earth. Those that fear neither radiation, poisons, nor the vacuum of space. Those who seem born for cosmic journeys. And then, the whole story takes a dizzying twist. All this time, we searched for signs of life in space. We stared into distant stars, studied meteorites, and sent rovers to Mars, hoping to find even a trace of alien organisms. We were explorers, observers. But that's not the whole truth. Wait, here comes a fact I double-checked several times because it sounds like science fiction. Despite all planetary protection protocols, achieving complete sterilization is impossible. That means we have already carried Earth life to Mars. An unknown but very real number of Earth's microorganisms have already touched down on the red planet. Starting with the Soviet Mars 2 probe, which crashed onto the surface back in 1971. Then the American Viking landers in 1976. In fact, every spacecraft that has ever landed there likely brought its own invisible stowaways. The Viking missions, Phoenix, Curiosity, all of them probably carried superbacteria from their sterile clean rooms. These microbes survived assembly, sterilization, and the long journey through space radiation. We were so worried about contaminating other worlds, we didn't realize we had already done it. We went from explorers to unintentional spreaders. This creates a massive challenge for future research. Imagine you're a detective arriving at a crime scene, only to find the entire investigation team has been wandering around in muddy boots for an hour, leaving footprints everywhere. Now, fast forward 10, 20, or even 50 years. We finally drill into Martian soil and discover microorganisms. How will we prove they're truly native Martian life, and not just descendants of bacteria hitching a ride on the Perseverance rover's wheels? Telling the difference could be nearly impossible. Our own excitement about exploring space might permanently close the door on one of humanity's biggest questions. Are we alone? Hidden within this problem lies a striking and ironic answer to our biggest question. The very fact that we, with all our technology and obsession with sterility, can't stop life from hitching a ride from one planet to another serves as the strongest indirect evidence for the reality of panspermia. In a way, we stumbled into an accidental experiment, and it came back positive. If humanity in the 21st century can't guarantee the sterilization of a single spacecraft, imagine nature. Nature had billions of years and trillions of asteroids and comets zipping between planets. Our failure to keep things perfectly clean proves one thing. Transferring life through space isn't just possible, it's probably inevitable. The circle has closed. We started by asking if life could have arrived on Earth from elsewhere. Now, we are the ones sending it to other planets. We searched for signs of panspermia, and in the process, we became its agents. So what do we really know for sure today? And where do we go from here to separate solid evidence from bold but unproven theories? So what's the bottom line? After this journey through asteroid fields, icy comets, and sterile laboratories, it's time to be honest. First and foremost, panspermia doesn't answer the big question. It doesn't explain how life emerges from non-living chemistry. This hypothesis only suggests that an event of this magnitude might have happened somewhere other than Earth, and that life, or its essential ingredients, were brought here afterward. It's not a solution to the mystery, it just shifts the mystery elsewhere. But right here, on this line, guesses end, and what we can test begins. What science has proven. First, the building blocks of life, amino acids, nucleotides, and complex organic molecules, aren't rare Earth anomalies. They spread throughout the cosmos. We found them inside meteorites that landed on Earth. We've detected their spectral fingerprints in massive clouds of interstellar gas and dust. And we know comets and asteroids have been delivering this material to planets, including early Earth, for billions of years. That's a proven fact. Second, some Earth organisms can survive conditions strikingly similar to interplanetary travel. More than just a few, they are true survival champions. Tardigrades and bacteria that endure vacuum, radiation, and extreme temperatures. This means lithopanspermia, the transfer of life inside rocks, is technically possible, at least within a single star system.
So what's next? Right now, missions are underway to tackle three big questions.
First, is there life, or at least traces of it, hidden deep beneath the Martian surface, beyond the reach of lethal radiation? Second, what secrets lie inside the cores of comets from the distant Kuiper Belt, these time capsules preserving material from the birth of our solar system? And third, the most thrilling of all, what will the analysis of the next interstellar visitor reveal? Just like Oumuamua, it will arrive from somewhere else in our galactic neighborhood. Each of these questions marks a crucial step toward discovery. While we wait for those answers, there's one truth we can grasp right now, and it might be the most important thing we've been searching for. No matter where or how the first living cell emerged, whether on Earth, Mars, or around a distant star, the chemistry at its core is universal. It spreads across the entire cosmos. The carbon atoms in our skin, the nitrogen in our genetic code, the iron in our blood, they all formed deep inside stars that died long ago. The molecules that make up our bodies once drifted as dust through the very interstellar clouds that eventually collapsed to form our sun and planets. We don't just live in the universe, we are the universe, briefly awakened, able to look back at itself and ask questions. We are woven from the same cosmic fabric as the stars. And that, perhaps, is the most profound conclusion any inquiry can reach.